main thing I remember was the noise of the earthquakes. It was something else to see the dawn come up that next morning, because of course there was no power or anything.
I was standing outside in the corridor there, yeah. And this building performed well, but yeah, it was quite an experience to go through.
The February one was during the day. I was actually at work with Fletcher EQR at the time, so yeah, we were out there trying to pull down chimneys and stuff the day after and try and make people's houses as safe as they could be.
Any major disaster heightens public awareness of the issues surrounding that event. For us, it was, I guess, not unexpected in a way. We knew that this would happen. I mean, if you live in New Zealand, you've got to accept that earthquakes will happen. They will affect our cities, and it's about preparing those cities as best we can for those events. We've learnt a lot from Christchurch, as you do from every event, and that's defining how we move forward, and the new structures lab is an integral component of that.
Most laboratories are quite small. Really, they can only test small parts of structures, a beam and a column together or a small part of a wall. That gave us a good idea of what was happening with a particular element, and we would synthesise that into design. But over the years, prior to the earthquake, there were some quite large structures built here at Canterbury and a couple in Auckland, which were mimicking the three-dimensional nature of a building, frames on both sides, big piece of concrete floors, and these were pushed around under a simulated earthquake as best as they could. The gear was very limited. That really opened our eyes to, we have to actually not just test a small column and a beam, we actually have to test large chunks of full-size structures. And then the earthquake came along and it was just like a massive gong went off. Things we saw there, we recognised once we saw it, but we'd never seen in the lab, or we'd only seen hints of it in the laboratory in these small specimens. That confirming that you actually got to go to large, full-size pieces of structure, and hopefully testing at a rate that's a loading rate or a pace that's akin to a real live earthquake.
Roughly a 500 square metre strong floor, and sitting on top of that you've got concrete walls that stretch to just over 9 metres in height. Those walls are 1.6 metres thick. The strong floor is approximately 2 metres deep, and built into those walls are a whole series of anchors. There's literally thousands of anchors built into the walls and floor, which enable us to bolt structures onto them. So we can load the structures and they don't move because the walls and the floor are holding them in place. They move because of the loads that we're placing on them. And we'll be putting in high-speed actuators, sophisticated hydraulic systems, which will drive the loading of these structures in a realistic way. It's really about being big and being able to load quickly, so it's fast and big.
When you got chosen for the concept of how we built it, Grant Thomas, my construction manager, spent a lot of time sketching up different aspects of the project as we progressed. And then he gave that to me and said, here you go, you've actually got to go and make this work on site.
This is an incredibly complex building. It is not a traditional commercial building, which is complex enough in their own right. This is an order of magnitude more complex.
We started with the BIM model by placing all the reinforcing in, then trying to fit all the trusses that support the couplers into the model, and then put the reinforcing in, and then we'd have to work out, is there any space left for the concrete to get into the bottom. We started off by placing in the bottom mat, followed by all the trusses that support the couplers, and at the same stage we had to do the vertical wall steel that supports the big walls, and then we also had to then do all the links so that we could then put the top mat in and double up the links through to form the reinforced cage of the floor. It was obviously very complex to fit all the couplers and stuff in amongst all the reinforcing, and to have so many layers of reinforcing and then so many tonnage. It was a very hard project to set out and get all the detail right in it. We weren't just bending the bars in 2 dimensions, we were bending them in 2 dimensions and then a 3rd dimension, getting them through, turning them down. So there's a real knack that the reinforcing guys had to work out of. There was a lot of man hours used up in the project trying to get everything into the right position.
When you bolt a structure onto the floor and you start loading that structure, it's essential that the bolt breaks before the floor breaks, or the bolt breaks before the wall breaks, because otherwise we start compromising the future of the facility.
In an informal review, it was discovered that the hold down bolts, basically the bolt itself just wasn't wide enough. When the bolt in the floor got loaded, the concrete around the hold down bolt would shatter. So what we needed to do was spread that force over a wider area of concrete. So what you needed was a bolt that had a shaft about that diameter. So what they did was they actually got hold of some circular steel, drilled a hole through the centre and pushed the already made sleeve into it. So when it got loaded, it didn't crush the concrete. So every single connection had to be retrofitted with this big sleeve. It was about 105 diameter and about 200 long. Had to be retrofitted and installed because that increased the weight, which made the temporary formwork really work hard. We had some interesting challenges on terms of getting them in the right place.
Yeah, made it even more difficult to fit the reinforcing around. The key was the bin model, where we could actually quite easily go in, increase the size of the coupler that was modelled into the bin model, and it showed us where all the clashes were that we had to then go back and resolve. Around the ends of the walls, as you can see, they're quite dense and complex, and at some stage we thought we weren't going to fit all the couplers in, but by all sorts of methods of getting down inside the walls and jimmying things apart, we just managed to slide them in. So it was a great feeling as the last coupler slid into its position on the outside formwork, and we could then close up the back formwork and prepare the shutters, square them all up and line them all up for the actual pour.
There are real issues with large pieces of concrete full of reinforcing. That's getting the concrete in.
What we found on the bottom was that we couldn't effectively vibrate the concrete. So with Firth we developed our layer cake method, where we started at the bottom with some self-compacting concrete, so we didn't have to worry about vibrating that as much. It's a really runny mix and it will fill any void it can find. And then once we got out of the very congested bottom mat, then we started with our bulk fill 40 MPa, and we got in there and we could effectively get down through a reinforcing to vibrate that. And of course at the top where we had the couplers, they wanted the ultra strong 65 MPa around the couplers to improve the shear capacity of the couplers. So that's how we got our layer cake of self-compacting, bulk fill MPa and 65 MPa concrete on the top.
Concrete goes hard through chemical reaction. That chemical reaction called hydration has a lot of heat. So one of the big problems was if the concrete gets too hot, it changes the minerals inside and the concrete can actually be damaged.
Yeah, so that's why they couldn't have gone 65 MPa throughout the whole depth of the slab, because the heat generated by that much concrete would have ended up with all sorts of thermal cracking. The floor was poured first in a 12-hour pour starting at 1 o'clock in the morning. We had 3 pumps here placing the concrete. So it took roughly about 10.5 hours to place the concrete, and of course then there's about an hour and a half of screening off and stuff to finish.
Intense is an understatement. I swear the contractors had a bottle of whiskey in the site hut. They had trucks standing in the street waiting to deliver. They had very well managed. They had pump trucks, pumping the concrete in, but they also had spare trucks. The whole thing was very, very well run. But it's one of these things, once they started, they couldn't stop. So Dominion had a very good quality assurance program which allowed them to deal with the odd thing that went wrong, trucks delayed, breakdowns on pumps and so forth. So that they were able to manage the heat. They had thermocouples for monitoring the temperature throughout the pour, and they stay right on the range that they were actually looking for.
Then we started on the walls, and the walls were done in 3 lifts. Just the volume of concrete and the weight, we could only support so much concrete going up each time.
The wall had its own special concrete because the reinforcing was different, but then again the chemistry was being controlled such that the heat of hydration didn't damage the concrete. The end product is pretty well right on the exactly what we were looking for.
It's been a challenging job to be involved with, but it's been rewarding in the same respect.
I have great pleasure in declaring the Structural Engineering Laboratory at the University of Canterbury officially open.
If you look back at our history, the department has played a major role in developing design codes, and the impact of that has been substantial in protecting life, human life, when there are major events. And the primary focus in the past has been to get people out, make it safe enough that people can get out. But what we've learnt from Christchurch is that while that we've been effective in that regard in most cases, there's a big focus now on developing buildings that are more readily repairable, so that we don't end up with this massive bill after a major event, which puts a strain on the community and also on the country as a whole.
Out of the Canterbury earthquakes, there was the Royal Commission. And the Royal Commission listed over 150 odd structural engineering questions. And so the quicker we can get through the Royal Commission questions, which again this hall is going to expedite, that's what I'm looking forward to. And also further down the line, we are visualising the bigger structures going in to deal with some of the retrofit details suggested for New Zealand, and also some of the new building systems, low damage buildings, again can only really be validated in a large building in a large test hall. So it's off the response and need that the New Zealand community has. There's some really good planned research coming down the line, so I'm as keen as hell to see it us to get on with it.